Notice I'm saying electrons equals photons. Right, divided by 3.1.
If it was efficiency, then you just multiply that.
You multiply a number of photons by 0.7 or something like that. We'll do one just like that. Divided by 3.1.
Wait, wouldn't it be the other?
Yeah,
You divide by the
divide by
0.7.
That's just basically photons
Times by
per square
1.3.
meter. It's an exposure is what it is, right?
No,
You know,
it's not the same.
this would correspond to a darkening of the film or an intensity of an image, right? This is, I'm getting 6.9
1.4
times 10 to the 14th photons per square meter.
2.8.
Which hearteningly is what I got last year when I made this.
Oh, yeah, you're right. There's 14
Now what's going to happen, obviously the dim light has fewer photons per square meter, right? So what happens as you increase the pixels, number of pixels in a camera, what happens to the amount of light hitting each individual pixel? I think it decreases because the area gets smaller, right? Doesn't it? Yeah. So one of the things that goes on is as you start packing more and more pixels into the CCD device, right? If they're all the same size, if the sensor is the same size, right? Then each pixel is getting less light per pixel. So therefore you've got to do something to boost the gain, and that's why these cameras are getting more and more expensive. That's the race, right? When this camera came out, they hadn't quite won that race, so they packed more pixels in, but this thing is not as sensitive to light as the camera I had before, which would shoot like 1024 by 768 or something like that, right? It would shoot that resolution, which was considerably less, right? But it shot crisp images in dim light. It could use fast shutter speeds because it didn't need much time to saturate the device. But this one needs more time, so when you guys are jumping from cart to cart out in the hall, and all those pictures are all blurred because there wasn't much light. Casey?
So do less photons per square meter, does that like
Fewer.
correspond to, or I guess fewer, yeah.
Yeah, I know, because you can count them.
Would that correspond to like less resolution in pictures, or is that?
No, that's fewer photons, just dimmer light, right?
Oh.
Yeah, yeah. So fewer is dimmer. So let's look at CCD devices. A sunny day, by the way, is about 3 times 10 to the 21st photons per second per square meter at 550 nanometers. So, yeah. And my sister talks that way. She's the solar engineer. So she'll look outside and go, it's got to be like a 200 watt per square meter day today. People don't talk that way, Gene. Here's a CCD device, and without getting into like solid state technology, you know, which I've forgotten. The photons come in here, and there's things on here that aren't sensitive to the light. So it's not like the entire area is available to detect the light. But the basic idea is that you eject. These are semiconductors, and you're ejecting electrons from the semiconductors, which makes electron holes, which are like positive charges. They move around, they talk funny like that. They're driven deep down into this layer, and they're stored as a voltage. They're like capacitors, they're stored like voltage, right? And you read them as voltage, okay? And then there's things on here so we can reset the pixel and clear the voltage on there. And then we can actually shift these things. So here is a picture, and we'll talk about the shifting here in a second. It's a sort of a shifty thing, right? Okay, but the voltage has to be converted to digital. So these are really analog sensors, which is kind of neat. I mean, think vinyl record. Don't think, you know, memory chip with accessible pixels. Yes, sir.
What do they do to boost the light gain?
Okay, yeah, we'll get to that slide, right? The second thing you need to know is that CCD devices are black and white. All they detect is light or no light. Okay, they don't detect color, and so this is called a Bayer mosaic, and there's red, green, and blue filters on there, right? And you can do a little image math with this, right? The green is kind of in the middle, the blue and the red are on either end, so there's more green pixels, right? Just, you know, there we have it, right? And if you look at the little sensor or pixel that's behind the red filter, blue light is not going to make it through the red filter, right? So this one is, if there's a red thing on there, this one's going to pick up more light, and this one less light, right? Does that make sense? And so if you're clever and you analyze the relative intensities of those different pixels, you can make color from that, right? There's an algorithm for this. There's some computer program that's in your camera, and that's what it's doing in between shots. Yeah.
So are CCD devices what make up photovoltaic multiple size? Like,
No, there's something similar going on though. It's a real basic. There's just raw. You're moving the electrons from a lower energy to a higher energy, and you just pull it off as voltage. It's very similar. Yeah, it's very similar, but this is more refined.
okay.
Okay. So anyway, this is the concept. Right? So color CCD devices aren't really color. They just put little filters, little things in front of them. On the Hubble telescope, they need to make 3 exposures, and they've got filters they can put in front of it. Yeah. So they take a red picture of the same thing, a green picture, and a blue picture, and then they do math with that. Right? If you extract raw data from your camera, right? Basically, you just get this raw pixel data, and then you have to put it into Photoshop and do all that math in Photoshop with it. My brother gets into doing that, and apparently you can get some really crazy results with it. If you just get the JPEG off of the camera, it does all that for you. So raw pictures are way, way more data than that, right? Okay. So we achieve the color with filters, right? And then here's the question about, you know, all the processing that goes on, right? Okay. Here's how it works. It's crazy. You take a picture, boom, you expose it. The camera opens and shuts. There's an aperture that you can adjust, big or small, for the light intensity, right? That lets the light in there. Also adjusts the depth of field and all that stuff, right? The picture's on there. It's stored on there, just like this capacitor can store charge. It can stay on there relatively a long time. Yes. Okay. Now, what you do is this is called a shift register, right? These things are shifted onto this register. Then those voltages, those little charges are shifted this way. Okay, so you're picturing that, they all go ka-chunk into there. Then you shift them this way, and right here, you've got an analog to digital converter, but you have got an amplifier there. So, if you've got a lot of pixels, there's not much voltage on there, is there? Because there's not much charge, not many photons have hit each individual pixel, right? Okay, so you have to boost that up. You've got, like, basically this is an analog amplifier, just like a stereo amp, right? It's taking a signal and just boosting it up, right? Then you've got analog to digital conversion, right? Then you've got JPEG compression and all that stuff where you take the raw data from those pixels, knowing which ones are blue, which ones are green, right? All that stuff, right? You do all that math, you can turn it into a JPEG, compress it, put it on a memory card. Any camera is probably, any digital camera is probably represents the computing power of the entire world in 1970, right? I mean, just imagine all that stuff that's going on. That's why cameras, cheap cameras like that one, have a considerable amount of time between when I take a picture and when I can take another picture. Because all of that's got to happen between each picture, right? That's why when you spend $5,000 on a camera, you can go click, 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 and just keep taking pictures because it's got a real fast processor. All of that stuff is high-end stuff, right? And so that's, you know, part of the stuff you're paying for. You've got a question.
How would you, when you input the image, are you doing with the numbers themselves?
Yeah, this is software. This is a computer that's taking those numbers, applying an algorithm like Photoshop does to it and constructing colors.
When it inputs it, does it take it like from like the highest number and then subtracts it?
Yeah, I don't know exactly what those algorithms are. They're not, you know, people that get paid a lot more money than me have figured all that out, right? Okay, but yeah, beyond here, it's all digital, right? This is the most exciting part, is, you know, the computing power of the world in the 1970s right here, right? Right? This camera has a mode, interestingly enough, where you can take 5 pictures really quickly and then you wait like 30 seconds, right? So what it must do is take all that data, dump it raw into RAM, which you can do fast, and then you wait while it processes picture, 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 right? You know, so to shoot really fast shots, that's what it does. But, you know, if you spend $5,000 on a camera, it'll take a picture every 20th of a second and store it, do all that stuff. That's amazing. To me, that's amazing. Doesn't that seem amazing? Yeah. Be amazed. Okay?
Ooh. Baby monkey?
No baby monkey. I don't know if we're going to get to it. Okay. Here's our camera. Obviously, the lenses on the camera have to take the image, and we talk about magnification, but really it's smallification. The image actually gets a lot smaller when it's put on the CCD device. I can take a picture of a house, but my CCD device might be like that big, right? Okay. And then here's the Nikon D3x here. It uses actually a CMOS sensor, right? CMOS sensors are far more digital. You can actually access the entire, you could access a particular pixel on a CMOS sensor without having to shift them down and do all this stuff, right? So I don't know if it's the way of the future, but it's a radically different sensor. And the Nikon D3x has 24 million pixels. The human eye has roughly 121 million pixels.